example, let's say we want to evaluate this integral using our method of partial fraction decomposition. Now the first step is to fully factor polynomial, our denominator, and I get stuck. I get stuck because I cannot factor x squared plus 1. So we cannot apply method 1 or method 2 to this because we cannot split our denominator into linear terms. This means we'll need a third method that handles quadratic polynomials like x squared plus 1 that don't split into linear terms. Alright, so in this video I'll tell you how to tell that a quadratic polynomial doesn't split. Alright, so let's first let me take p of x to be ax squared plus bx plus c. So some quadratic polynomial. First, I'll say that p of x is irreducible. If I can't factor it in linear terms, but there's going to be an easier way to say this. It's irreducible if p of x does not have zeros. Right? So it doesn't pass through the x-axis. Its graph doesn't cut through the x-axis, so no values of x will give us p of x equals 0. The reason why I say this is easier to say is now we have a test. We have the quadratic formula that gives us a formula for the 0. So that formula cannot make sense. And so what we'll do is we'll call b squared minus 4ac. That's the interior of the square root in the quadratic formula. That's the only place where that formula can go wrong. If that's negative, then you won't have any zeros. So this is an important number. It's called the discriminant of p of x. Alright, so what we're after is this fact. P of x is irreducible exactly when its discriminant is less than 0. So if the discriminant is less than 0, then you'll have a square root of a negative number. That doesn't work over the real, so that means I won't have any zeros and p of x will be irreducible. So let's try it on x squared plus 1. B is 0, there's no linear term. A is the coefficient of x squared, that's 1. C is the constant term, that's 1 as well. I get minus 4, I get a negative discriminant. And so, indeed, x squared plus 1 is irreducible.